In this notebook, we start with an introduction to PyTorch and its ecosystem, then compare it with other frameworks like TensorFlow. We also look at real-world use cases in research and industry. Next, we set up the environment, including installation for both CPU and GPU, working with CUDA, and setting up notebooks or IDEs like Jupyter and VS Code. We then cover core PyTorch concepts, working with Tensors, using the Autograd engine, and building neural networks with torch.nn. You'll learn how to define models, add layers and activation functions, and train them using forward and backward passes, loss functions, and optimizers. We also explore data handling with datasets and DataLoaders, as well as model evaluation using accuracy, precision, recall, and the confusion matrix. Finally, we show how to save and load models properly using PyTorch best practices. By the end of this video, you'll be ready to build, train, and evaluate neural networks in PyTorch. Introduction to PyTorch. Welcome to the PyTorch series. In this slide, we'll get a quick overview of PyTorch and its ecosystem. PyTorch is an open-source deep learning framework developed by Meta, formerly known as Facebook. It's known for its flexibility, ease of use, and strong community support. Unlike some other frameworks, PyTorch uses dynamic computation graphs. This makes it very intuitive for Python developers and especially powerful for research and rapid prototyping. It is widely used in both academia and industry. Many top AI research papers and production systems are built using PyTorch. The core library includes several important modules. Torch is the base package that handles tensors and computation. Torch.nn provides tools to build neural networks. Torch.Autograd enables automatic differentiation for training. Torch.optim includes popular optimization algorithms like stochastic gradient descent and atom. PyTorch also has excellent support for GPU acceleration using CUDA. The ecosystem includes helper libraries like Torch Vision for image data, Torch Audio for speech and sound, Torch Text for natural language processing, PyTorch Lightning for easier training loops, and integration with Hugging Face for using transformer-based models. Together, these tools make PyTorch a complete and powerful platform for deep learning. In this slide, we'll compare PyTorch with other deep learning frameworks, especially TensorFlow. One key difference is how they handle computation graphs. PyTorch uses dynamic computation graphs. This means the graph is built at runtime, making it more flexible and easier to debug. TensorFlow originally used static graphs. The graph had to be defined before running the model. This made it less intuitive, especially for Python developers. However, TensorFlow 2.0 introduced eager execution, which is more dynamic. PyTorch code feels more Pythonic. It blends naturally with native Python syntax and control flow like loops and conditions. This makes it a favorite among researchers and those new to deep learning. On the other hand, TensorFlow has more mature tools for deployment. For example, TensorFlow Lite allows models to run on mobile devices. TensorFlow Serving makes it easier to serve models in production environments. Historically, TensorFlow was preferred in production, while PyTorch dominated research and education. But this gap is closing fast. Today, many production systems also use PyTorch, especially with tools like TorchScript and TorchServe. In summary, PyTorch stands out for flexibility and ease of development, while TensorFlow may offer more deployment features out of the box. The choice often depends on your specific project needs. Now let's look at where PyTorch is used in the real world, both in research and industry. In research, PyTorch is a go-to framework. It's widely used in natural language processing, computer vision, and reinforcement learning. Many academic papers and top conferences use PyTorch for model development. In industry, PyTorch is used in sectors like automation, healthcare, finance, and robotics. Companies use it for real-world tasks like object detection, fraud detection, speech recognition, and medical imaging. Major tech companies like Meta, Tesla, Microsoft, and OpenAI use PyTorch at scale. In fact, many large-scale models such as GPT, DALL-E, and Clip were built using PyTorch. What makes PyTorch especially valuable is its support for fast prototyping. You can design and test new architectures quickly, which is essential in both research labs and fast-moving startups. At the same time, PyTorch scales well. You can start on a single laptop and move to powerful cloud GPUs or distributed systems when needed. This makes PyTorch a versatile tool, good for experimentation and ready for production. Setting up the environment. In this slide, we'll learn how to install PyTorch both for CPU and GPU setups. The easiest way to get the correct install command is to visit the official PyTorch website. There's an install page where you select your preferences, like Python version, operating system, and whether you want GPU support. PyTorch supports both pip and conda for installation. Choose the one that matches your environment or your team's workflow. If you only plan to use your CPU, installation is very straightforward. You can simply run a pip or conda command, and you're ready to go. For GPU acceleration, you'll need to install a version of PyTorch that includes CUDA support. CUDA is a toolkit by NVIDIA that lets PyTorch run operations on the GPU. Make sure your GPU is compatible and that the installed CUDA version matches the one supported by PyTorch. Once installed, you can check if GPU support is active by running the following command: import torch, print torch.cuda.is available. If the result is true, PyTorch has detected your GPU and is ready to use it. If it prints false, you're running on CPU or the GPU setup isn't correctly configured. In this slide, we'll explore how PyTorch uses CUDA for GPU acceleration. CUDA is a platform by NVIDIA that allows PyTorch to run computations on the GPU. Using CUDA can significantly accelerate training and inference compared to using only the CPU. To take advantage of the GPU, we need to move both the model and the data to the GPU memory. This is done using methods like .cuda or .to, which we'll see on the next slide. The torch.device object is useful when writing code that should work on either CPU or GPU. This makes your code more flexible and easier to deploy across environments. Before using the GPU, always check if CUDA is available using torch.cuda.is_available. To monitor your GPU's performance, use the command line tool called envidia-ssmi. It shows the GPU's memory usage and active processes. Overall, if you have a supported NVIDIA GPU, using CUDA with PyTorch will give you a big speed boost for model training. Let's go through this code step by step to understand how GPU acceleration works in practice. First, we import the torch library. We check if CUDA is available by calling torch.cuda.is_available. This returns true if a compatible GPU is available, or false otherwise. Next, we create a random tensor on the CPU using torch.randn. To move this tensor to the GPU, we use the .cuda method. This allocates the tensor on the GPU memory. Alternatively, we can define a device object using torch.device. This lets us write flexible code that works on both CPU and GPU, depending on what's available. We then move the tensor using .to and pass in the device. This is the recommended method in most real-world applications. Finally, we print the device to confirm where the tensor is stored, either CUDA 0 or CPU. Using this pattern ensures your code runs efficiently and is hardware-aware. In this slide, we'll look at how to set up your environment for working with PyTorch using either Jupyter Notebooks or Visual Studio Code. Jupyter Notebooks are highly interactive and great for quick experiments tutorials, and visualizations. They let you write and run code in cells, which is ideal for exploring ideas and debugging in small steps. On the other hand, Visual Studio Code, also called VS Code, is a full-featured integrated development environment. It offers excellent support for Python, PyTorch, and other tools. It's better suited for writing larger projects, building classes, managing files, and debugging with breakpoints. To install Jupyter, you can simply run pip install notebook. Then you can start it with the command Jupyter Notebook. In VS Code, make sure to install the Python extension from Microsoft. You can also add the official PyTorch extension to get syntax support, code completion, and debugging tools tailored for PyTorch development. In short, use notebooks when you're experimenting or learning, and switch to VS Code when you're building something more structured or production-ready. Core concepts of PyTorch. In this slide, we'll cover what tensors are and how they work in PyTorch. Tensors are the fundamental data structures in PyTorch. They're similar to NumPy arrays, but with built-in support for GPU acceleration. You can think of them as multi-dimensional arrays. They can represent scalars, vectors, matrices, or higher-dimensional data. PyTorch makes it easy to create tensors using functions like torch.tensor, torch.rand, torch.zeros, and others. Each function helps generate tensors with different values and shapes. Once you have a tensor, you can perform mathematical operations like addition, multiplication, matrix multiplication, and averaging. Tensors are also flexible. You can reshape them, slice them, change their data types, or move them between devices like CPU and GPU. Understanding tensors is the foundation for everything you'll do in PyTorch, including building and training models. Let's walk through this code to see how to create and manipulate tensors. We start by importing Torch. We create a one-dimensional tensor using torch.tensor, a two-dimensional tensor of zeros using torch.zeros, and a random 2x2 tensor with torch.rand. Next, we perform some mathematical operations. We add 1 to every element in tensor A. We also multiply each element by 2. For matrix multiplication, we use torch.matmul on two compatible tensors. We reshape a tensor using .view. In this example, we change a one-dimensional tensor into a column vector with 3 rows and 1 column. Finally, we move the tensor to the GPU using the .to method. We first define a device based on whether CUDA is available. Then we call a .to with the device. The print statement shows where the tensor is stored, on the GPU or on the CPU. These operations form the basics of how you work with data in PyTorch. In this slide, we'll learn about Autograd, PyTorch's automatic differentiation engine. Autograd tracks all operations performed on tensors. This makes it possible to automatically compute gradients, which are essential for training neural networks. When you create a tensor with requires_grad set to true, PyTorch will record any operations performed on that tensor. This allows it to build a computation graph behind the scenes. When you call the backward function, PyTorch uses the chain rule to calculate gradients for all tensors involved in the computation. The resulting gradient for each tensor is stored in its .grad attribute. This system makes it easy to compute gradients without writing complex derivative code manually. It's a core part of how backpropagation works in neural network training. Let's walk through this simple example of using Autograd. We start by importing Torch. Next, we define a tensor x with requires_grad set to true. This tells PyTorch to track all operations on x. We define a simple function y equal to x squared plus 3 times x. Then, we call y.backward. This triggers PyTorch to compute the derivative of y with respect to x. Finally, we print x.grad. This gives us the gradient of y at the point x equals 2. The result is 7 because the derivative of x squared plus 3x is 2x plus 3. And when x is 2, that equals 4 plus 3, which is 7. This is how PyTorch handles gradient computation automatically using Autograd. A computation graph is like a map of operations your deep learning model will do. Each node in the graph is a math operation like addition, multiplication, or matrix multiplication. The edges, arrows, show how data flows from one operation to the next. This graph tells the computer how to calculate the result and how to go backward for training with backpropagation. PyTorch sees that you're doing x times x. It records this operation in a graph. Then it sees plus 3 and adds another step to the graph. So the graph is built automatically while the Python code runs. In old TensorFlow, you had to define the whole graph first. First, you must only describe the graph. Then you had to run it. So the graph is fixed and must be built before running. Building neural networks. In this slide, we'll explore the torch.nn module, a powerful part of PyTorch that helps you build neural networks easily. Torch.nn provides everything you need to define and train models, including layers, activation functions, and loss functions. At the heart of it is the nn.module class. This is the base class for all models in PyTorch. You'll either subclass it to build custom models or use nn.sequential for simple models. Common layers include nn.linear for fully connected layers, nn.conv2d for convolutional layers, and nn.relu for activation functions. These layers are designed to work smoothly with Autograd, so gradients are automatically computed during backpropagation. Torch.nn is also designed to work well with the Optim module and the training loop, which we'll see in later slides. Let's see how we can use torch.nn to define a simple neural network. We start by importing torch and torch.nn. Then we define a model using nn.sequential. This is a convenient way to stack layers in order. In this example, we create a fully connected network with an input layer of size 10, a hidden layer of size 20, followed by a ReLU activation, and an output layer that produces a single value. We print the model to see its structure. Next, we create a batch of 5 input samples, each with 10 features, using torch.randn. We pass the input through the model to get the output. Finally, we print the shape of the output. It shows 5 rows and 1 column, meaning 1 output for each input sample. This is how torch.nn helps us define and use neural networks in PyTorch. In this slide, we'll learn how to define a custom model in PyTorch by subclassing nn.module. Instead of stacking layers with nn.sequential, we define our own class that inherits from nn.module. This gives us more flexibility for complex architectures or custom logic. Inside the init method, we define all the layers and components we need. We must call super.__init__ to properly initialize the base class. Next, we define the forward method. This is where we describe how the input flows through the layers and activation functions. This approach gives us full control over the architecture, and it integrates perfectly with PyTorch's automatic differentiation and optimizers. Now let's look at an example. Here's an example of defining a model using the nn.module approach. We start by creating a class called SimpleNet that inherits from nn.module. Inside the init method, we define 2 fully connected layers and 1 ReLU activation. The first layer takes 10 inputs and outputs 20. The second layer reduces that to 1 output. We use super.init to call the parent class constructor. In the forward method, we define how data flows through the network. Input goes through the first linear layer, then the ReLU activation, and finally through the second linear layer. Next, we instantiate the model and create a batch of 5 input samples, each with 10 features. We run a forward pass by calling the model with the input tensor. Finally, we print the shape of the output, which is 5 by 1, one result for each sample in the batch. This pattern is the most common way to define flexible, real-world models in PyTorch. You don't call forward directly, because with model input tensor, under the hood, PyTorch automatically calls the forward method for you. This is possible because the nn.module class implements the call method, which handles things like hooks, device, data type checks, and so on, then internally calls your custom forward method. In this slide, we'll cover layers, activation functions, and the sequential API in PyTorch. Layers are the basic units that make up a neural network. Common layers include nn.linear for fully connected layers, nn.conv2d for convolutional layers, and nn.lstm for recurrent models. After each layer, we often apply an activation function. Activations introduce nonlinearity, which helps neural networks learn complex patterns. Popular activation functions include ReLU, sigmoid, and tanh. For simple model architectures, we can use nn.sequential. This API allows us to stack layers and activations in the order they should be executed. Sequential models are great for quick experiments and fast prototyping. But for more complex logic, we use a custom class that inherits from nn.module. Now let's go over the most commonly used layers in PyTorch and their important parameters. nn.linear is the fully connected layer. It takes in features and out features as arguments, and optionally, a bias term. nn.conv1d and nn.conv2d are used for convolution operations in 1 or 2 dimensions. You provide the number of input channels, output channels, kernel size, stride, and optional padding. For sequence data, PyTorch provides nn.rnn, nn.lstm, and nn.gru. Are used in natural language processing and time series tasks. They typically take input size, hidden size, and the number of layers. nn.batchnorm1d and nn.batchnorm2d normalize activations during training, helping models train faster and generalize better. nn.dropout randomly sets some activations to 0 during training. This helps reduce overfitting. The default drop probability is 0.5. For embedding categorical inputs, nn.embedding is used. It maps each index to a learnable vector of fixed dimension. And for activation functions, PyTorch provides nn.ReLU, nn.sigmoid, and nn.tanh. These layers usually don't require any arguments. This table gives you a quick reference to most layers you'll use when building networks in PyTorch. Use the linear layer when you need a fully connected layer, typically in feed-forward neural networks, classifiers, or the final output layer of models. It is often used after convolution layers to make predictions from extracted features. Use convolution layers for feature extraction, especially with structured data like images, audio, or signals. Conv1d is used for sequential data like audio signals. Conv2d is standard in image classification, object detection, and computer vision tasks. These layers are ideal for modeling sequences. Use them in time series forecasting, text processing, and natural language understanding. LSTM and GRU are more powerful than a plain RNN because they handle long-term dependencies better. Batch normalization is useful to stabilize and speed up training. Use batchnorm1d for linear layers or sequence data. Use batchnorm2d after convolution layers in image models. Use dropout to prevent overfitting by randomly dropping units during training. It's common in fully connected layers, especially before the output layer of classification networks. Use embedding layers when dealing with categorical input data, like words or tokens. It maps each category or token to a dense vector and is a key part of NLP models. Use ReLU in most hidden layers for faster training and sparse activations. Use sigmoid or tan-H in special cases. For example, in binary classification, use sigmoid in the final layer. Use tan-H when you want output centered around 0, especially in RNN-based models. Training a model. In this slide, we'll understand the forward and backward pass in PyTorch training. The forward pass is when we feed input through the model to compute predictions. These predictions are then compared to the true values using a loss function, which gives us the error. Next comes the backward pass. This is when we calculate how much each weight contributed to the error. PyTorch handles this using its automatic differentiation engine called Autograd. We start the backward pass by calling .backward on the loss. This computes gradients of the loss with respect to each parameter. The gradients are stored in the .grad attribute of each parameter. Then the optimizer uses these gradients to adjust the model weights so the predictions improve in the next iteration. Let's now see how this works in a real training step. Here's a basic example of the forward and backward pass in PyTorch. We define a simple model using nn.sequential with one linear layer that takes 3 inputs and outputs 1 value. We create one input tensor and its corresponding target. We define a mean squared error loss function and use stochastic gradient descent as the optimizer. In the forward pass, we pass the input through the model to get predictions. We compute the loss between the prediction and the true value. To perform the backward pass, we call .backward on the loss. PyTorch now calculates all the gradients automatically. Then we call optimizer.step to update the model parameters using the gradients. Finally, we reset the gradients to 0 with optimizer.zeroGrad, so the next step starts fresh. This forward and backward process repeats for each batch during training. nn.mse loss, or mean squared error, is used in regression problems where the target values are continuous numbers. It measures the squared difference between predicted and true values. nn.l1 loss, or mean absolute error, is also used for regression. It's less sensitive to outliers because it takes the absolute difference rather than the square. nn.bce loss, or binary cross entropy, is used for binary classification problems. The model output should be a probability between 0 and 1, typically after a sigmoid activation. nn.bce with Logit's loss combines sigmoid activation and binary cross entropy in one operation. It is more numerically stable and should be preferred when using raw outputs. nn.cross entropy loss is the most common choice for multi-class classification. It expects raw class scores, called logits, and automatically applies softmax and negative log likelihood internally. nn.nll loss, or negative log likelihood loss, also works for multi-class classification, but expects that you have already applied a log softmax to the model output. nn.multi-margin loss is a hinge-style loss, often used with SVM-like classifiers. Understanding which loss to use is critical for getting correct and stable training behavior. Next, we'll demonstrate a few of these loss functions with example code. Let's see how to use some common loss functions in PyTorch through real examples. We begin with mean squared error. We pass in a predicted value and a target value. The loss is 0.25, which is the square of the difference between 2.5 and 3. Next, we use binary cross entropy. We give it a predicted probability of 0.9 and the target of 1. It computes how far the prediction is from the ideal probability. Lower values mean better confidence. If your model outputs raw scores instead of probabilities, use BCE with Logit's loss. This function applies the sigmoid internally and is more stable. For multi-class classification, we use cross-entropy loss. We provide raw logits and the target class index. The function applies softmax and computes the log loss internally. Let's explore some of the most important optimizers in PyTorch, their key features, and when to use them. First is SGD, or stochastic gradient descent. It is simple and effective. It can be enhanced with momentum to speed up training and weight decay for regularization. Use SGD when training from scratch or for fine-tuning pre-trained models. Atom is one of the most popular optimizers. It uses adaptive learning rates and converges quickly. It's a great default choice for most deep learning tasks, including image and text applications. RMSprop adjusts the learning rate for each parameter individually, based on recent gradient magnitudes. It works well with recurrent models and when the gradients are noisy or unstable. Autograd is useful when features appear infrequently. It gives large updates to rare features and is often used in natural language tasks with large vocabularies. AdaDelta is an improvement over Autograd. It does not require a manually defined learning rate and is good for model. Finally, AtomW is a variant of Atom with proper weight decay handling. It is preferred in transformer models and other large-scale deep learning applications. These optimizers are available in the torch.optim module and can be easily switched in your training loop. Let's walk through how to define different optimizers in PyTorch. We start by creating a simple linear model with 10 input features and 1 output. For SGD, we use the torch.optim.sgd class. We specify the learning rate, momentum, and weight decay. Next is Atom. We initialize it with a learning rate of 0.001. This optimizer adapts learning rates for each parameter. RMSprop is created similarly. We can adjust the smoothing constant alpha to control how it averages gradients. Autograd increases learning rates for rarely updated weights. It's often used for sparse data, and we just set the learning rate. AdaDelta is another variant that adapts learning rates over time. It often works well without manually tuning the learning rate. Finally, AtomW is widely used in transformer models and is preferred when using weight decay properly. Each optimizer is initialized with the model's parameters, and you can swap them in your training loop depending on your task. This slide introduces gradient clipping and learning rate schedulers, two techniques that improve training stability and performance. First, gradient clipping is used to prevent gradients from becoming too large during backpropagation. When gradients explode, they can make the model weights unstable, especially in recurrent neural networks or deep models. In PyTorch, you can use clip-grad norm to scale down gradients that exceed a specified norm. You can also use clip-grad value to clamp gradient values within a fixed range. Next, learning rate schedulers dynamically adjust the learning rate during training. They help the optimizer converge faster or avoid getting stuck in local minima. There are several types. Step LR decreases the learning rate by a factor every fixed number of epochs. Exponential LR applies continuous decay. Reduce LR on plateau lowers the learning rate when validation performance stops improving. Cosine annealing smoothly decreases the learning rate and can help with cyclical learning strategies. These tools are essential for training deep models efficiently and with stability. Next, let's see them in action with real code. Let's walk through the code for gradient clipping and learning rate scheduling in PyTorch. First, we define a linear model and an SGD optimizer. After calling backward on the loss, we use clip-grad norm to prevent the gradients from exceeding 1.0. This keeps training stable and avoids large, destructive updates to the model. You can also use clip-grad value if you want to directly cap individual gradient values. Next, we define several learning rate schedulers. Step LR reduces the learning rate every 10 epochs by multiplying it with 0.1. Exponential LR continuously shrinks the learning rate by multiplying it with 0.9 each epoch. Reduce LR on plateau monitors a validation metric, such as loss. If the metric stops improving for a number of epochs, it reduces the learning rate. Cosine annealing slowly decreases the learning rate in a cosine curve, which can help the model settle into better minima. Inside the training loop, we compute the loss, apply gradient clipping, perform the optimizer step, and then call the scheduler's step function. This approach makes training safer, smoother, and more likely to converge successfully. Data handling in PyTorch. PyTorch provides two essential classes for managing data: dataset and DataLoader. The dataset class is used to define how your data is loaded. You typically subclass it and override two methods. The first is dunder_len, which returns the number of samples. The second is dunder_getItem, which returns a single data sample, often as a tensor and label pair. You can use dataset to load data from images, CSV files, or even from a database. Once you define your dataset, wrap it with the DataLoader class. DataLoader automatically handles batching, shuffling, and parallel data loading using multiple CPU cores. You can control the behavior of the loader using parameters like batch size, shuffle, and number of workers. This separation between data logic and loading logic gives you both flexibility and speed. Let's now look at an example to see how dataset and DataLoader work in code. Let's walk through a basic example of using dataset and DataLoader in PyTorch. First, we define a class called myDataset that inherits from torch.utils.data.dataset. Inside the constructor, we store the data and labels. The dunder_len method returns the number of samples. The dunder_getItem method takes an index and returns the data sample and its label. Next, we create random data with 100 samples and 10 features, and random binary labels. We create a dataset instance by passing the data and labels. Then we wrap it in a data loader, setting the batch size to 16, enabling shuffling, and setting number of workers to 0. Now, when we loop through the data loader, it gives us batches of 16 samples at a time. We print the shapes of the feature batch and label batch to confirm that everything works. This is the standard way to handle custom datasets in PyTorch. When you're working with your own data in PyTorch, you often need to create a custom dataset class. To do this, you subclass torch.utils.data.dataset and implement two methods, dunder_len and dunder_getItem. The dunder_len method returns how many samples are in your dataset. The dunder_getItem method returns a single sample, typically the input and label, and optionally applies preprocessing. For preprocessing, PyTorch provides a powerful set of tools in torch_vision.transforms. Some commonly used transforms include toTensor, which converts images to PyTorch tensors, normalize to scale values, resize, random crop, and random horizontal flip, which are useful for data augmentation in computer vision tasks. To apply multiple transforms together, you can use transforms.compose, which lets you chain transformations in order. These transforms are typically applied inside the dunder_getItem method when returning each sample. Let's now look at a full code example using a custom image dataset and transforms. Here's how you define a custom dataset class for loading images with transforms. We create a class called image_dataset that inherits from torch.utils.data.dataset. The constructor takes the path to a folder of images and an optional transform pipeline. The dunder_len method returns the number of images in the folder. In the dunder_getItem method, we load an image using Pillow and convert it to RGB format. If a transform is provided, we apply it to the image. For now, we return a placeholder label of 0, but in real use, you would extract the correct label here. Next, we define a transform pipeline using transforms.compose. This pipeline resizes the image to 128 by 128 pixels, randomly flips it horizontally for data augmentation, converts it to a tensor, and normalizes pixel values to a range around 0. We then create a dataset using our image folder and transform pipeline. Finally, we wrap it in a data loader with a batch size of 8 and shuffling enabled. When we iterate through the data loader, we get batches of transformed image tensors ready for training. When loading data with PyTorch, you can control batching, shuffling, and parallel loading using the data loader. Batching means grouping several samples together into a single batch. This speeds up training by taking advantage of vectorized operations on the CPU or GPU. Shuffling randomly changes the order of the samples each epoch. This helps prevent the model from learning any accidental sequence patterns in the data and improves generalization. Parallel loading allows you to load data using multiple CPU processes. This speeds up data access, especially for large datasets or slow storage devices. These behaviors are controlled using DataLoader parameters. Batch size sets how many samples per batch. Shuffle equals true enables shuffling each epoch. Number of workers sets how many subprocesses to use for data loading. If your dataset size is not divisible by the batch size, you can use drop last equals true to discard the final smaller batch. Let's look at a simple example that demonstrates how these options affect the data loading behavior. Let's see how to use batching, shuffling, and parallel loading in code. First, we create a simple tensor dataset with 10 samples, where the data and labels are just numbers from 0 to 9. We create a data loader with a batch size of 3, shuffling enabled, number of workers set to 0, and drop last set to true so that the final incomplete batch is discarded. Now, when we loop over the data loader, we get batches of 3 samples, and the order is different each time because of the shuffling. The output shows the randomized batches. In real training, you would increase the number of workers to 2 or 4 for faster data loading, especially when reading from disk. This is how you control batching and data loading behavior using PyTorch's data loader. It is important to mention that torch.range10 creates a 1D tensor. The method .reshape -1, 1 turns it into a 2D tensor. 10 is the number of samples, and 1 is number of features per sample. .view -1, on the other hand, flattens or reshapes any tensor into 1D vector for easier printing or processing. Model evaluation and metrics. When evaluating a model, especially for classification tasks, it's important to go beyond simple accuracy. Let's understand 4 common metrics: accuracy, precision, recall, and F1 score. Accuracy is the number of correct predictions divided by the total number of predictions. It works well when all classes are balanced. Precision measures how many of the predicted positives are actually correct. It is calculated as true positives divided by the sum of true positives and false positives. High precision means fewer false alarms. Recall measures how many of the actual positives your model successfully found. It is calculated as true positives divided by the sum of true positives and false negatives. High recall means fewer missed detections. F1 score balances precision and recall. It is the harmonic mean of the two and gives a single number that accounts for both kinds of error. In cases of imbalanced data, such as detecting fraud or disease, accuracy alone can be misleading. That's when these other metrics become essential. You can calculate all of them using scikit-learn's metrics module. They support both binary and multi-class classification. Let's now look at a code example that shows how to calculate these metrics. Here's a simple code example using scikit-learn to calculate accuracy, precision, recall, and F1 score. We first import the required functions from sklearn.metrics. We define two lists, one for the true labels and one for the model's predicted labels. We pass these lists to each scoring function. Then we print the results, rounding to 2 decimal places. In this case, the accuracy is 0.75, which means 75% of the predictions were correct. Precision, recall, and F1 score are also all 0.75, indicating balanced performance. These metrics give you a much clearer view of your model's performance, especially when class distributions are not even. Let's explore 2 more important tools to evaluate your models: the confusion matrix and the ROC-AUC score. The confusion matrix is a summary table that shows how well your model performed. It displays 4 values: true positives, correctly predicted positives; true negatives, correctly predicted negatives; false positives, wrongly predicted as positive; false negatives, wrongly predicted as negative. By analyzing these values, you can better understand where your model makes mistakes. For example, is it generating too many false positives or missing actual positives? The ROC curve, which stands for Receiver Operating Characteristic, plots the true positive rate against the false positive rate at different thresholds. The AUC, or area under the ROC curve, is a number between 0 and 1. The higher the AUC, the better your classifier is at separating the classes. A perfect classifier has an AUC of 1.0, while a random guess gives an AUC of 0.5. Scikit-learn provides built-in functions like confusion matrix, ROC curve, and ROC-AUC score to generate these evaluations easily. Now let's look at a code example. In this example, we calculate and display both the confusion matrix and the ROC-AUC score. We define the true labels, the predicted classes, and the predicted probabilities. We use confusion_matrix to print the confusion matrix. The matrix shows 3 true negatives, 1 false positive, 1 false negative, and 3 true positives. Next, we calculate the ROC curve using ROC_curve. This gives us the false positive rate, the true positive rate, and the thresholds. Then we calculate the area under the ROC curve using ROC_AUC_score. The result is 0.94, which is a high score. It means our model is performing well in separating the 2 classes. Optionally, we can plot the ROC curve using matplotlib. Together, the confusion matrix and ROC-AUC score give a complete picture of model performance, especially for binary classification. When training machine learning models, it's important to separate your dataset into distinct parts. The 2 most common splits are the validation set and the test set. The validation set is used during training. It helps you tune hyperparameters, evaluate overfitting, and select the best model version. The test set, on the other hand, is used only once, after training is complete. It simulates real-world, unseen data. You should never use the test set during training or model selection. To avoid information leakage, these splits must stay completely independent from each other. A common split is 80% for training, 10% for validation, and 10% for testing, or you may use a 70-15-15 split depending on your data size. You can split data using train-test-split from scikit-learn, or use stratified k-fold when you need balanced class distributions across folds. Let's now see a short code example. In this example, we split a dataset of 100 items into training, validation, and test sets. We first split the data into a training set and a temporary set using train_test_split. We set aside 30% of the data for validation and testing. Then we split that temporary set again, 50-50, into validation and test sets. Finally, we print the sizes. The result is 70 samples for training, 15 for validation, and 15 for testing. This ensures that we have clean, separate subsets for each stage of the machine learning pipeline. It is worth mentioning that the random state parameter controls the shuffling applied to the data before splitting. It ensures that the split is reproducible, meaning that every time you run this code with the same random state, you'll get the same train-test split. Saving and loading models. To save your trained PyTorch model, you should use the function torch.save. However, instead of saving the full model object, you usually save only the model's state dictionary. That means all the parameters and weights, without the model structure. You do this by calling model.state_dict and then pass it to torch.save. This approach is more flexible and more portable. The convention is to save the file with a .pt or .pth extension. Later, you can load the weights back into the same model architecture using load_state_dict. This keeps your save file small and lets you modify or rebuild the model later if needed. Now let's look at a code example. Here, we define a symbol model using the linear layer from torch.nn. After creating an instance of the model, we save its weights by calling torch.save and passing in model.state_dict. We store it in a file named model_weights.pth. This saves only the trained parameters, not the model architecture. This is the recommended way for most use cases. The print statement confirms that the weights were saved successfully. To use a saved PyTorch model, you need to load the weights into a new model instance. First, create the model architecture exactly as it was when saved. Then call load_state_dict and pass in the loaded weights. If you're using the model for inference only, remember to call model.eval. This sets the model to evaluation mode, turning off things like dropout and batch normalization updates. If you're resuming training, call model.train instead. Also, if you save the optimizer state, you can reload it to continue training exactly where you left off. Let's walk through the code. In this example, we define the same model structure we used earlier when saving the weights. Then we call torch.load to read the saved weights and pass the result to model.load_state_dict. Finally, since we're going to use the model for inference, we switch it to evaluation mode using model.eval. This disables layers like dropout and ensures consistent predictions. The print statement confirms the model is ready for inference. When saving PyTorch models, follow these best practices to ensure reliability and flexibility. First, always prefer saving only the state dictionary using model.state_dict. This keeps your saved file clean and makes it easier to load and adapt in different projects. Stick with standard file extensions like .pt or .pth so others know it's a PyTorch model. Also, save or document the model class and architecture definition. You will need the exact structure when loading the weights. If you plan to resume training later, you should also save the optimizer state dictionary as well as any relevant metadata, like the training epoch, loss history, or learning rate. Avoid saving the entire model object using torch.save model. It captures both code and weights, but it ties your model to the Python environment and may break if code changes. Now let's look at a complete save and resume pattern in code. Here we define a simple model and an atom optimizer. We save a full training checkpoint as a Python dictionary. It includes the current training epoch, the model state dictionary, the optimizer state dictionary, and the last loss value. We then pass the dictionary to torch.save and write it to a file called checkpoint.pth. This way, everything needed to resume training is saved in one place. You can later load this dictionary and restore your model, optimizer, and training state. A complete example. We begin by importing all the required libraries for building and training our PyTorch model. From scikit-learn, we import modules to load the breast cancer dataset, split it into training and testing sets, and normalize its features. Then we import PyTorch modules for building the neural network, training it, and loading data efficiently. This includes the neural network module, the optimizer module, and the DataLoader utilities. We also import NumPy for compatibility with common array operations, although we mostly work with PyTorch tensors. This setup ensures we have all necessary tools to pre-process data, define the model, and train and evaluate it properly. We now load the breast cancer dataset from scikit-learn. This dataset contains medical features extracted from tumor images, and the target label indicates whether the tumor is malignant or benign. We extract the input features into the variable called capital X, and the target labels into the variable called lowercase y. Next, we normalize the input features using standard scalar. This standardizes the values so that each feature has a mean of 0 and a standard deviation of 1. Normalization is important for faster convergence during training. We then split the dataset into a training set and a testing set. We use 80% of the data for training and 20% for testing. The random state is fixed for reproducibility. After that, we convert the NumPy arrays to PyTorch tensors. We use float32 as the data type for the input features and long integers for the target labels, which is required when using cross-entropy loss. In this step, we prepare our data for training and testing using PyTorch's DataLoader. We first wrap our training and testing tensors using tensor dataset. This allows PyTorch to pair each input feature vector with its corresponding label. Then, we use the DataLoader class to create batches from our datasets. We set the batch size to 32, which means each iteration processes 32 samples at once. We enable shuffling for the training data, which helps the model generalize better by varying the input order each epoch. For the test data, we keep the order fixed by disabling shuffling. Using DataLoader makes it easier to loop through data efficiently, especially when training on large datasets or using GPUs. Here we define the structure of our neural network model. We create a class named Breast Cancer Net that inherits from nn.module. This is the base class for all PyTorch models. Inside the constructor, we define a sequential container called classifier. The model starts with a linear layer that maps the 30 input features to 64 hidden units. Then, we apply a ReLU activation function to introduce nonlinearity. Next, we add another linear layer that maps 64 units to 32, followed by another ReLU. Finally, we add a third linear layer that maps 32 units to 2 output classes. Since we are doing binary classification, we use 2 output units, one for each class. We do not apply softmax here because cross-entropy loss expects raw logits. The forward method simply runs the input through the classifier pipeline. We then instantiate the model by calling breast cancer net. Now we define the loss function and the optimizer. We use cross-entropy loss from torch.nn. This loss function combines log softmax and negative log likelihood loss, making it suitable for multi-class classification tasks. Even in binary classification, it is used when the model outputs logits for 2 classes. Next, we create the optimizer using ADAM. ADAM is short for adaptive moment estimation, and it adjusts learning rates individually for each parameter. We pass the model's parameters to the optimizer and set the learning rate to 0.001. This setup allows us to minimize the loss by updating the model's weights using gradient descent. We now train the model over a loop of 20 epochs. Each epoch means one full pass through the entire training dataset. We first set the model to training mode using model.train. This enables behaviors like dropout and batch normalization if used. For each batch in the training data, we perform the following steps. First, we zero the gradients using optimizer.zeroGrad. This is necessary because PyTorch accumulates gradients by default. Then, we perform a forward pass by passing the input batch to the model. This gives us the raw outputs or logits. We compute the loss between the predictions and the ground truth labels. Next, we perform the backward pass using loss.backward. This calculates the gradients of the loss with respect to each model parameter. Finally, we call optimizer.step to update the weights based on the computed gradients. We accumulate the batch loss to monitor training performance and print the loss after each epoch. After training, we evaluate the model's performance on the test set. We first set the model to evaluation mode using model.eval. This disables training-specific behaviors like dropout. We also disable gradient tracking using torch.nograd. This reduces memory usage and speeds up computation during inference. For each batch in the test set, we pass the inputs through the model to get predictions. Since the model outputs logits, we use torch.argmax along dimension 1 to get the predicted class index. We collect the true and predicted labels into lists. Finally, we compute the test accuracy using scikit-learn's accuracy score function. This tells us how many samples were correctly classified out of all the test samples.
Thanks for watching.